today numerical 3 on moment of inertia. This numerical is different from previous two numericals, and difference is previous two numericals x-axis is symmetrical upward side and downward side. X-axis is symmetrical upward side this side and downward side this side, and y axis is also symmetrical in previous numericals. But here see, this y-axis is symmetrical. The right side of y-axis and left side of y-axis both symmetrical, but this x-axis upward side and downward side are not symmetrical. So here parallel axis theorem we use for calculation of moment of inertia of this section, this rectangular section with this hollow rectangular part inside it. So due to this unsymmetry in x-axis upward side and downward side, solving methodology is different for this numerical. Centroid of this original section is centroid of this original section x and y is equal to, first consider this full rectangle. That means hatch portion is hollow part. First consider full rectangle with depth 100 mm, capital D depth 100 mm, and small b, capital B, breadth 60 mm. And from this rectangular moment of inertia, subtract this hollow part moment of inertia. This is solving methodology of this numerical. So area of this rectangle is A1 and area of this rectangular part is A2. So first consider A1 area. Area for this rectangular is D into B, that means 100 mm by 60 mm. That means 6000 mm square. And this their small part area is small d 20 mm and small b also 20 mm. Depth and breadth d into b, 20 into 20, 400 mm square. Position of neutral axis for this rectangular part is y1 from this bottom face, and for this small square part, this is not rectangular part, sorry, this is square part. For small square part is y2, and our ultimate aim or our aim is to solve for this section moment of inertia. And for solving this section moment of inertia, we consider this whole rectangular part and deduct this small square part. This is solving methodology. And original neutral axis of this rectangular part is different. This is not y1 or not y2. This is different. That means this is y bar. So first, to find original neutral axis from bottom of this section, for this we first calculate neutral axis of this section. That means First calculate y1. Neutral axis for this section is denoted by y1 and neutral axis of this square section is denoted by y2. Y1 neutral axis from bottom. From bottom, that means this from bottom. Y1 neutral axis is 100 by 2. A1 is area, Y1 is neutral axis. 100 by 2 is 50 mm. Area is denoted by mm. Area unit is mm square and neutral axis Y1 unit is mm. And neutral axis for this section, that means for this part is nothing but this part here. See, original section is 20 by 2 plus 20 plus 25 plus 20 because this part is also included from bottom, and 20 by 2 is this part. That means y2 is equal to 20 by 2 plus 20, 30 mm. And to calculate original section neutral axis, y bar is equal to formula. Y bar is equal to a1 y1 minus y minus, because we have to consider deduct this part. This part is not, this is hollow part. That means remove this part. That means minus a2 y2 upon area. Area is also a1 minus a2. That means a1 y1 minus a2 y2 upon a1 minus y1. a1 minus a2, sorry, a1 minus a2. a1 is 6000 multiplied by y1 is 50 minus a2 is 400 multiplied by y2 is 30 upon a1 minus a2, 6000 minus 400. So neutral axis for this original section is 6000 into 50 minus 400 into 30 upon 6000 minus 400 is 51.43 mm. So see, this y bar comes 51.43 mm. And this y1 neutral axis is 50 mm. And this y2 neutral axis for the square section is 30 mm. So to solve moment of inertia for this whole rectangular part, neutral axis is not this 50 mm, not y1 mm. Neutral axis is this 51.43 mm, because we have to find moment of inertia for this section. Our aim is to finding for this section, and for this section neutral axis is 51.43 mm, not 50 mm. So solve here y bar. That means from this y1 to some distance. So here parallel axis theorem comes. So see, and for this rectangular part also moment of inertia find about this 51.43 mm neutral axis. This is x-axis, so consider for this rectangular part axis is x1 x1 and for this square part axis is x2 x2, and our aim is to find for this. So ixx moment of inertia about x axis. X axis is this original section axis xx, and for this rectangular part is ix x1 minus the square part x2 x2. Ixx1 is moment of inertia for this axis, this original rectangle and original neutral axis for this rectangular part. First, this is parallel axis theorem. See our previous lecture for grasp concept of parallel axis theorem. Capital B capital D cube by 12 plus area of this rectangle A1 into y bar minus y1 square, and this part BD cube by 12 is moment of inertia about this rectangle original axis. This rectangle original axis is original centroidal axis is 50 mm. See my previous lecture about parallel axis theorem, then you grasp this concept very fastly. Small d cube by 12 plus the square part area is A2 multiply by y bar minus y2 square. 160. Here B is 60. 60 into 100 cube divided by 12 multiply by A1 is 6000 multiply by y bar is 51.43 minus y1 is y1 original neutral axis for this rectangular part 50 mm and square of it minus 20 side of square is 20 into 20 cube divided by 12 plus A2 is 400 multiply by y bar 51.43 minus y2 is 30 mm. So moment of inertia about x axis for this original section is 60 into 100 cube divided by 12 plus 6000. Here see plus sign and we write here multiply sign, so wrong, here plus sign, plus 6000 into 51.43 minus 50 square minus 20 into 20 cube divided by 12 plus 400 into 51.43 minus 30 square. So moment of inertia Ixx is 4.815 into 10 raised to 6. 4.815 into 10 raised to 6, and unit of moment of inertia is mm raised to 4. So why this much calculation we require and we take? Because of this section or this body is not symmetrical about x-axis, so we require parallel axis theorem. So when body is not symmetrical about x-axis, then we require parallel axis theorem. And body is symmetrical about x-axis, then our work is easy. Directly we use formula BD cube by 12 for calculating moment of inertia. But here, due to unsymmetry, our task becomes hard. Now see about this y-y axis. See right side and left side. This y-y axis, right side and left side, both sections are symmetric. So for this IYY axis calculation, our work is easy. For calculation of IYY, see IYY is equal to I y1 y1 minus I y2 y2. This y1 y1 is this rectangular part. Neutral axis y1 y1, sorry y1 y1 and y2 y2. So I y1 y1 is capital B capital D cube by 12 minus small b small d cube by 12. And neutral axis is also neutral. There is not eccentricity for neutral axis about y axis. Here symmetry, so neutral axis comes from centroid. Due to x-axis unsymmetry, there is eccentricity in neutral axis, but here not. Neutral axis is passing through centroid, so BD cube. So this body neutral axis, this body neutral axis, and this body neutral axis is same. So that's why here not parallel axis theorem we use. BD cube by 12. B is 60 into 100 cube by 12. Minus square, sorry here square, okay, square moment of inertia. This is square moment of inertia is a raised to 4 by 12. So here I think we make mistake. We consider this rectangular area BD cube by 12, but here a raised to 4 by 12 is square moment of inertia. But our answer and our step is correct. Why correct? Because 20 raised to 4 or 20 into 20 raised to 3 is same. See, 20 raised to 4 side square by 12 or 20 into 20 raised to 3 by 12 is same. Both are same. Only here write like this, side raised to 4, 20 raised to 4. Okay. Here also side square, right side square, side raised to 4, sorry, right side raised to 4, square side raised to 4, and here also square side raised to 4, side of rectangular part, and side of rectangular part is 20 mm, 20 raised to 4 by 12. So IYY for this body is 60 into 100 cube, sorry 60 here BD cube by 12, B is 60, B is 100. See, we make mistake for this also. About y okay. About y axis, moment of inertia is not bd cube by 12. It is db cube by 10. See, moment of inertia about this y axis. Parallel to y axis is this d. So take d first, and then take opposite side db cube by 12. First is parallel side of this y axis db cube by 12 minus small d minus here side square by 12, side raised to 4 by 12. So d is 100 multiplied by 60 cube divided by 12 minus side of square is 20 raised to 4 divided by 12. So 100 into 60 cube divided by 12 minus 20 raised to 4 divided by 12 is 1.7867. 1.7867 into 10 raised to 6 mm raised to 4. This is IYY. So moment of inertia about this x-axis is greater value than moment of inertia about this y-axis. See, moment of inertia about this x-axis 4.815 into 10 raised to 6 mm raised to 4, and moment of inertia about this IYY is 1.7867 into 10 raised to 6 for rectangular and this square part deduction. X moment of inertia is greater value and YY moment of inertia is smaller value, because deduction between both axes are same. See this YY axis left side deduction is 10 mm by 20 mm rectangular part, and right side 10 mm by 20 mm rectangular part. Although this x-axis is unsymmetrical, so although this x-axis is unsymmetrical, then also moment of inertia about x-axis is greater value, and moment of inertia about y axis is small value as compared to ix. Thank you very much.